OpenAI RAN promises more flexible and intelligent mobile networks. But that flexibility also creates a reliability challenge. My project focuses on one practical question: how can we continuously understand what is happening inside an OpenAI RAN system, detect performance problems early, and explain their likely causes before users are seriously affected? In an OpenAI RAN environment, performance depends on many moving parts: radio conditions, software components, compute resources, scheduling decisions, and user mobility. A problem may not appear as a complete failure. It may start as small performance degradation, such as higher delay, lower throughput, unstable radio quality, or overloaded resources. Detecting these early requires more than static thresholds. The first step is reliable telemetry collection. In OpenAI RAN, performance issues can come from different parts of the system. Some problems are related to the radio link, such as signal quality, scheduling, or throughput. Other problems come from the computing platform, such as CPU pressure, memory usage, interrupts, or processing delays. Looking at only one side gives an incomplete picture. That is why this project collects both radio telemetry and platform telemetry. Raw telemetry alone is not enough. The system needs to turn many low-level measurements into a useful representation of network health. To do this, the telemetry is aligned over time, cleaned, and combined into a live snapshot of system behavior. Instead of relying on a single metric, the monitoring pipeline looks at patterns across many signals together. This makes it possible to detect performance anomalies more intelligently. The second step is performance anomaly detection. The goal is not only to recognize complete failures. In many cases, problems begin as gradual degradation. Throughput drops, resource usage increases, radio conditions become unstable, or protocol behavior changes. The detector learns what normal operation looks like and compares live telemetry against that normal pattern. When the difference becomes significant and persistent, the system raises an anomaly alert. This helps avoid reacting to short temporary fluctuations. A key challenge is that normal behavior depends on context. A highly loaded network does not look the same as a lightly loaded one. A stable radio environment does not look the same as a mobility-heavy or interference-heavy environment. Because of this, one generic detector may confuse unusual but acceptable behavior with real problems. This project uses context-aware monitoring. First, understand the operating situation, then apply detection logic that is better suited to that situation. The third step is root cause analysis. Detection alone does not solve the operational problem. An alert that says something is wrong still leaves the operator asking, "Where should I look first?" The root cause analysis component identifies which telemetry signals contributed most to the anomaly and maps them back to meaningful parts of the radio access network system. For example, the likely cause may be related to scheduling, radio quality, protocol behavior, or platform resource pressure. This turns a black box warning into actionable evidence. Together, these components form a reliability loop for OpenAI RAN. The system observes the network through reliable telemetry. It detects abnormal performance behavior early. It explains the likely root causes. And it supports future adaptation, recovery, and model improvement. This changes monitoring from a reactive process into a proactive and explainable one. In summary, this project aims to make OpenAI RAN operation more trustworthy. By combining reliable telemetry collection, performance anomaly detection, and root cause analysis, the system helps operators understand not only when the network is degrading, but also why it may be happening. This is an important step toward AI-enabled radio access networks that are observable, reliable, and explainable.